Welcome back, grade 9. I am absolutely thrilled to have you here for today's explainer because we are tackling something massive. We're unpacking one of the most fundamental rules of the entire universe. I mean, have you ever actually stopped to wonder why things move the exact way they do? Or, why they sometimes just stubbornly refuse to move at all? Well, today we are putting on our scientist hats to master the physics of motion. We're going to bring a ton of energy and laser-like focus to the invisible rules that govern our physical world. Let's get right into it. Okay, picture this. Imagine you're riding on a fast-moving bus. You're standing up, maybe you're just holding onto a rail. Suddenly, the driver hits the brakes. What happens to your body? Just take a quick mental beat to predict it. You fly forward, right? Your body completely lurches toward the front of the bus, even though you definitely didn't consciously decide to move. And conversely, if the bus is parked and suddenly hits the gas, your body gets shoved backward. You feel this invisible pull. But what exactly is it? Well, that invisible feeling is exactly what we're decoding today. Here is our roadmap for mastering motion. First, we'll look at the magic of inertia. Second, defining Newton's first law. Third, visualizing forces in motion. Fourth, we'll explore mass and rotational inertia. Fifth, real-world applications. And finally, a quick pop quiz to test your knowledge.
All right, jumping right into section 1, the magic of inertia.
Before we look at any textbook definitions, we need to observe the physics happening right in front of us. So we're going to do a classic demonstration. It's called the coin drop challenge. Imagine a really simple setup. You've got a glass, a regular playing card resting flat on top of that glass, and a heavy coin resting right on top of the card. Now here is my question to you. If I sharply and quickly flick the edge of the card with my finger, what's going to happen? Will the coin fly away across the room with the card? What do you predict? Think about it for a second.
Okay, let's dive into this. When you flick that card sharply, the card flies away, but the heavy coin actually drops straight down into the glass with a super satisfying clink. But why didn't the coin fly away? Well, it's because of a physical property called inertia. Even though the card moved, the heavy coin basically wanted to stay right where it was, at rest. The card just slipped out from under it. Once that physical support was gone, gravity acted as an unbalanced force to just pull it straight down.
Moving right along to section 2, defining Newton's first law.
So, now that we've seen this concept in action, it's time to formalize it, and we're bringing in a true genius to help us out. Over 300 years ago, Sir Isaac Newton figured out the rules of how things move. He came up with 3 scientific laws, but today we are placing our focus entirely on his first one. Newton's first law of motion states, an object at rest stays at rest, and an object in motion stays in motion with the same speed and in the same direction unless acted upon by an unbalanced force. Let's actually break that down into everyday terms. A soccer ball sitting on the grass won't move until you kick it. Your kick is the unbalanced force. On the flip side, a rolling marble will just keep rolling forward forever unless an external unbalanced force, like friction, acts on it to slow it down. It literally resists changes to its state of motion.
Which brings us to section 3, visualizing forces in motion. Let's move to a virtual FET-Lab simulation and see how this builds. It's one thing to just talk about unbalanced forces, but it's incredibly helpful to visualize exactly how they interact with objects. When the net force acting on an object is 0, which basically means all the pushing and pulling forces are perfectly balanced out, the object is in what we call mechanical equilibrium. If it's resting, it stays resting. If there's no push or pull stronger than the other one, the object's velocity simply will not change. And this brilliantly illustrates what happens when we disturb that balance. Here, we're applying 100 newtons of force to a 50-kilogram box. If this applied push is greater than the static friction holding the box to the ground, boom, we have an unbalanced net force. The result? The box accelerates. Its state of motion changes completely because, well, we forced it to. Now, what's really interesting about this slide is how we can essentially make friction visible. Friction is an absolutely crucial force in everyday life. In our simulation, when you stop pushing the box, it doesn't just stop instantly, right? And it doesn't keep gliding forever either. The kinetic friction between the box and the ground acts as an unbalanced force in the opposite direction. Without friction, that box would literally just keep sliding at a constant speed infinitely. All right, on to section 4, mass and rotational inertia. This brings us to a really fascinating question. Do all objects have the exact same amount of inertia? Think about a ping pong ball and a bowling ball. Which one is harder to move? The bowling ball, right? Obviously because it's heavier. Mass is essentially a measure of inertia. The greater the mass, the harder it is to start moving and the harder it is to stop. But this gets even cooler when we look at objects that spin. Let's look at the egg spinning challenge. If you take a fresh, raw egg and a completely hard-boiled egg, and you try to spin them both on a table, which one do you predict is harder to start spinning? And if you quickly stop them both with your finger and then let go, which one will magically start spinning again all on its own? Take a second. Lock in your guess. The fresh egg is actually way harder to spin. But why? Well, because the liquid yolk inside a fresh egg has its own mass and it's loose in there. When you twist the shell, the heavy liquid inside just wants to stay at rest due to its inertia. It actively resists the spinning motion. But here is the crazy part. Once you finally get that fresh egg spinning, if you briefly stop the shell with your finger, the liquid yolk inside actually keeps spinning because of its inertia in motion. So when you let go, the moving yolk forces the shell to start spinning again. It's so cool. Let's shift gears to Section 5, Real-World Inertia Applications. Shifting from eggs to humans, let's anchor this back to real life and highlight exactly why this matters for your personal safety. Because inertia isn't just a classroom concept, it is quite literally a matter of life and death on the road. So the crucial point is this scenario here. Imagine a car traveling at 60 kilometers per hour. Because you were inside that car, your body is also traveling at 60 kilometers per hour. If that car suddenly hits a wall, the car stops instantly. But remember Newton's law? An object in motion stays in motion. Your body has inertia. It wants to keep moving forward at 60 kilometers per hour. If you aren't wearing a seatbelt, you'll just continue moving forward until you hit the dashboard or windshield. The seatbelt acts as the life-saving unbalanced external force required to stop your forward motion safely. And that brings us to Section 6, Pop Quiz. Let's test your knowledge. All right, grade 9, it is time to cement our learning. Get your mental pens and paper ready because we are jumping into a high-energy pop quiz. Let's see how well you've actually mastered the law of inertia. Here's your first question. Which property of an object determines how much inertia it has? Are your options A, volume, B, temperature, C, mass, or D, speed? Take a mental beat. Lock in your prediction. If you chose C, mass, you are absolutely correct. Mass is the direct measurement of inertia. The heavier the object, the stronger the inertia. This is exactly why a loaded, heavy school bus needs a significantly longer distance to hit the brakes and stop compared to someone just riding a lightweight bicycle. Okay, let's move to our final quiz question, tethering the physics directly back to your everyday lives. Why do we need to wear seatbelts? Your options are A, to look cool, B, because the seat is slippery, C, to increase the weight of the car, or D, to stop our inertia from throwing us forward during a crash. Final prediction, make it count. And the correct answer is, of course, D. We wear seatbelts to stop our inertia from throwing us forward. You've officially mastered how an unbalanced force stops your forward motion. Incredible job today. Before we wrap up this explainer, I want to leave you with one final, totally mind-bending thought to take with you. If Newton's first law dictates that an object in motion stays in motion forever, as long as there is no unbalanced force like friction or gravity to stop it, where in the vast universe could you throw a baseball and never ever see it stop? Imagine a spacecraft drifting at 100,000 meters per second in the deep, frictionless void of space. Without an opposing force, does motion truly last for eternity? Keep questioning, keep observing the forces around you, and whatever you do, don't let your mental inertia stop you from learning. See you next time.